Hi everybody, my name is Daniel Bloom. I am the current president of ISAC, the Information Security and Assurance Club, and Dr. Berkman asked me to record this presentation for him, so here I am. Let's get started. We're talking about Spectre and Meltdown Demystified. Alright, so what we'll learn is, one, what Spectre and Meltdown are. I'll give you some layman explanations and some technical explanations. These are pretty advanced vulnerabilities / attacks, so I'll try to explain it in a way that's good for people who know a lot about IT and care a lot about IT, and then also don't. So, yeah. And then we'll talk about the issues with patches and mitigations. And I have somewhat of a demo on this computer. I can't really do the live demo that I did in ISAC, but I can show you where I got it from, and I can explain it a little bit. Okay. So first, big vulnerabilities, get cool patches. I just decided to include this in my presentation. I think they're cool. You should think they're cool. Let's continue. Okay, so what are they? So Spectre and Meltdown are two critical vulnerabilities in modern processors that were found in late 2017 and they were released in early January of 2018. So they're super new. They allow malicious, users to steal data from processors that's not being directly processed by computers. So they can steal super secret, just sort of arbitrary data. They're super easy to exploit, and they can steal information from memory used by running programs as well as from privileged memory in the operating system. So they can steal passwords stored in password managers, messages that if you're using iMessage on your Mac, they can steal the messages and documents from Word, etc. And nearly every single device, sort of in general, is affected by one or both. Almost every processor since 1995 is vulnerable. So if you're playing on your phone, that phone is vulnerable. If you're sitting on your laptop, that laptop is vulnerable. So this applies to you. Okay, so we'll start with Meltdown, get you some general info. So what it does is it breaks the just most fundamental isolation between applications and the operating system. So what that means is that basically there's userland code and operating system code, which is privileged code and privileged memory, and Meltdown allows you to go from userland to privileged without any issue. I'm going to explain that more in a few slides, but that's the basic gist for right now. It allows attacks on just completely arbitrary system memory, so you can get pretty much anything that's on the system, any information, including user passwords, admin passwords, etc. And they're nearly both attacks are nearly undetectable. You can't. They leave no traces. You can't see them in modern AV systems, antivirus systems. So they're super hard to catch. So once if you've been attacked, sorry about you. The patches also significantly slow down CPUs, and I'll be explaining that a lot more later on as well. But the biggest thing to know here is that the CPU is actually functioning as advertised. Neither of these vulnerabilities really take advantage of a bug or anything. It's more just features, especially Meltdown. It's just a feature that has some side effects. And so Spectre, some general info on that, it breaks isolations between applications. So while, if you have Word open and the internet, your browser, Google Chrome or whatever, Google Chrome should not be able to see or touch the memory that's being used by Word. And iMessage can't see what's being used by, WhatsApp, etc. But with this attack, it can. It basically allows attackers to trick error-free, extremely secure programs into leaking secrets. And the worst part, safety checks and security systems actually increase the attack surface for this attack. So if you try to secure your app with crazy stuff, you're just making it worse. That's not to say you shouldn't have security. That's just to say this attack is super bad. Once again, nearly impossible to detect, can't be seen on AV, and it's extremely hard to patch. While Meltdown can be patched, it does slow down PCs. Spectre has some workarounds, but it's going to be a problem for a very long time. So let's start with Meltdown. So the way I'm going to do this presentation is I'll start with layman examples based on superheroes, because everybody everybody knows about superheroes, so it's all good. This presentation was based on an article I wrote that was published on Hacker Noon. If you want that information, I can say my email address at the end of this presentation. So, Meltdown in layman. So, let's say you're watching Justice League, and you're watching this scene where Batman's trying to recruit the Flash. So one day, Batman goes, he sits in the dark, and I don't know if you've seen Justice League, but he comes to the Flash's house, and he sort of sits in the dark. And then when he comes in, he's like, "Oh, I'm Batman. I've got a proposition for you." Let's say they're walking down the street, right? And Batman's like, "All right, now that you've joined the Justice League, I gotta tell you where the Batcave is." And so he whispers into the Flash's ear, and he says, "This is where the Batcave is. Don't tell anybody." Unbeknownst to both of them, the Joker has already installed super advanced listening devices all over the city. So the Joker now knows exactly where Batman's cave is, where the Batcave is. That's pretty much how Meltdown works. It allows for just super secret listening and very private information. And I'll explain that in a technical way right now. So first we got some prerequisite information that we need to go over before I can actually explain how the attack works. So first, privileged memory. So you've got the kernel code, which is your operating system, and that runs in privileged mode. While you also have userland application code, which runs in non-privileged mode. So anything that deals with the actually moving memory and dealing with the actual operating system backend is usually run in privileged mode, which means that it's got it's sort of like root access or admin access to your computer. And then userland code, which is just code written written for applications that the users can actually interface with directly, that should never be able to touch. It should never be able to touch privileged memory. It'll throw an exception or just fail with an error if it tries to access privileged memory or tries to perform privileged operations. Next, we've got out of order execution. This is really where the big bug comes in, so keep this in mind. Processors are pretty antsy. They don't really like to sit around and wait for instructions to finish. That's just not efficient, and processors really, really like efficiency. So what they do is they'll start instruction 1, and then as instruction 1 is running, they'll also start 2, 3, and 4. That way, you don't have to wait for 1 to finish, then 2 to finish, then 3 to finish, then 4 to finish, just to have 4 instructions completed. You can just do 1, then 2, 3, 4, then once 1 is done, 2 is finished, and then 3 and 4 are almost done. It's just more efficient. All right, prerequisites 2, page caching. This is also a pretty important piece. So computers, like I said, really like efficiency, and computers also don't really like to work too hard. So without caching, you'd have to... So first of all, imagine a computer without caching. So that I can explain what caching is. A computer has to go and search for bits of data in memory, right? And there's a lot of memory to search through. When a computer touches one of these bits of data, it'll cache it, which is basically like putting it in its pocket for quicker access. That way, later on, when it has to come back and get that information, it doesn't have to search through the entire computer again. It's just got that information in its pocket. And a cache page is 4,096 bytes. That's going to be important for the actual attack. And then exception handling. Like I said before, when a code throws an exception, it's just failing with an error. And when code catches an exception, it's handling the error and allowing the program to continue running. So, yeah. So when code throws an exception, it usually touches bits of privileged memory, but that doesn't really matter because there are privilege checks that should not allow that memory to be cached or be used by the actual userland application. But when errors are thrown, operating system code does run, and there are bits of privileged memory that are touched. So keep that in mind. So Meltdown, the problem. So first, out of order execution has some pretty observable side effects, which I'll go over in a bit. And then second, privilege mode checks and checks for privileged memory don't actually execute during out of order execution. So basically they don't execute on the non-focused instructions. So if you run instruction 1 and then you start 2, 3, and 4, instruction 1 is that focused instruction. So that's the one that is going to have privilege checks. But instructions 2, 3, and 4 don't have privilege checks on them. And then, not really a problem, but a thing to remember is that cache memory is easily accessible, and anything in the cache is non-privileged, so anybody can access anything in the cache. So let's see how it works. So first, the attacker will allocate 256 pages of memory. So what that means is that it'll take about 1.04 megabytes, and it'll say, this is where I'm going to search through. Remember, the pages won't be cached yet because they haven't been accessed. They've just been allocated. So allocation means like getting ready to access, pretty much. Next, a sequence of code called the sender is executed, and this has 4 steps. Now remember, these 4 steps will be run out of order because of processor efficiency. So first, the processor will start by performing an instruction that'll throw an exception. So it'll just do anything to cause an error. And then as that error is coming up, it'll read a byte from privileged memory. So remember that there's no privilege checks in out-of-order execution, so it's able to look for and read privileged memory. And then it'll multiply that byte by 4096, which is the cache page size. And then it'll use that value as an index into the block of allocated memory. So basically it takes this piece of privileged memory, multiplies it by the size of each page, and then uses that number to say, this is where I'm going to look for, like this is where I'm going to start looking in my large bank of allocated memory. So remember, like I said, CPU doesn't do privilege checks during out-of-order execution, so whenever it's executing steps 2 through 4, the attack will be able to run without any privilege checks. And then step 2 will be able to access privileged memory because of this lack of privilege checks. And once data gets touched, it gets cached. All right. So now, after that sender code runs, there's a receiver that tries to get that privileged information. So it caches the exception thrown by sender function instruction 1. So basically, it just allows the code to keep running. And it'll loop through every page in the allocated block of memory, and it'll perform a timing attack. So what a timing attack is it'll basically time how long it takes to read 1 byte from each page, and if one of the bytes loads, or if one of the pages loads faster than the other pages, then it'll know that that page has been cached. So that's the page with the information that we touched from step 2 in the sender function. Because the rest of the pages, the computer has to go out and search for the memory location, while the secret that we touched is cached. So after that, he knows the attacker knows exactly where this secret information is, and it can be easily read through the cache. And the attacker will just repeat the entire process, the sender and the receiver, as many times as they want. They can do about 1.8 gigabytes an hour. That means they can steal 1.8 gigabytes of completely privileged, completely arbitrary information every hour, which doesn't seem like a whole lot right now. But first of all, you could put a whole lot of information in 1.8 gigabytes. And second of all, a really well-guided attack could do this multiple times, and they could have hundreds of hours of just running, especially because it's so hard to catch. All right, so now let's go over Spectre. So Spectre's layman explanation. So when the Justice League isn't out, beating up aliens and fighting crime, they like to play hide and seek in Batman's super big mansion. So everybody knows how hide and seek is played. You've got one person standing in the living room or something, and the rest of them go out and hide, and you count, and you say, okay, ready or not, here I come. And then you go around and search manually for everybody. Today, it's Superman's turn to seek. And he just really doesn't want to play. He's just not about it. But, he got pressured into it, peer pressure, so here he is, he's playing. But instead of actually going around and searching, Superman just said, you know what, whatever, I'm just going to use my X-ray vision. So that's what he does. And because of that, he's able to see exactly where everybody is hiding, exactly what position they're in, and he's also able to see all of Bruce Wayne, that's Batman, all of Bruce Wayne's secret stuff, including his bespoke Superman action figure, which he definitely didn't want Superman to know about. So let's get some prerequisites down. So first, speculative and execution / branch prediction. This is a bit complicated. So, like I said before, computers really like efficiency, and they really don't like wasting time. So what branch prediction is, it's basically like the trolley problem, but with ghost trolleys. So everybody knows what the trolley problem is. You've got a train coming down the tracks, and you've got 5 people laying on the tracks on the right side and 1 person on the left side, and you have to flip a switch to change the train's direction. So when a computer looks at this problem and it says, I've got on the right side this code to execute and on the left side this code to execute. So like if true, execute this. If false, execute this. What do I do? So instead of waiting for the actual true or false statement to come in, what the computer will do is speculatively execute both branches. So it'll basically use a ghost trolley that isn't supposed to be able to really touch anything. It's supposed to just fly right through the people and not have any problems. And it's just supposed to be able to set up the instructions so that if the computer wants to go down that path, it's already pretty much ready to go down. And then if it doesn't want to go down the other path, the phantom trolley is supposed to just disappear. However, that's not really the case sometimes. So we'll discuss that in a second. But basically, the CPU will see a conditional statement and just go down both paths and reverse the instructions down the path that's not taken. So what's the problem? To speed up speculative execution, some combinations of operating system and hardware actually let speculative paths touch data in the operating system's private memory. So remember, data is cached whenever it's touched, and the ghost trolleys aren't really supposed to touch anything. But some combinations, i.e. most of our computers and phones, actually allow this to happen. So they allow the ghost trolleys to crash through walls and run people over, etc. And like I said, since speculative branch touched memory, it was cached, and resulting data cache is basically a covert channel. I won't be discussing covert channels too much in this, but I also wrote another article about it, so if you want to read that, I'll give you my email address at the end of this presentation. It's a covert channel through which attackers can extract information, once again using timing attacks. So like I explained before, what a timing attack is, you basically measure how long it takes for certain queries to respond. So if you query a piece of cached memory, it's going to respond faster than a piece of uncached memory because it's in the processor's pocket and the processor doesn't have to go out and search for it. So basically, Spectre forces programs to speculatively execute code branches that they don't normally want to execute. So executing, bad malicious code that shouldn't normally happen. And that way it tries to figure out exactly what private memory was cached by using timing attacks. So let's see how it works. So first, the attacker locates a sequence of code or just instructions within a process that can act as a covert channel. So basically, it looks for a conditional statement that it can use to, or it creates a conditional statement that it can use to access private memory if speculatively executed. Then it tricks the CPU into executing the instruction sequence. So let's see. Okay, so this is where we get a little bit technical. So right here, as you can see, we've got if x is less than array 1 size, y equals array 2 of array 1 of x times 256. So normally, I'll explain the code a little bit better in the next slide, but normally, if x is less than array 1 size, then you do that. If not, then you don't. And if you do it with x is over array 1 size, you're going to reach out of bounds memory, which is usually privileged or other application memory. So first, the attacker will train the CPU branch predictor to expect that this if statement results in true. So it'll just run it a bunch of times, like a few thousand times, with x is less than array 1 size, so that it just thinks that it's true. So it'll keep, when it speculatively executes, it'll say, all right, this is probably true. I'll run some code down the true branch. Then the attacker gives an x value bigger than the array 1 size to get out of bounds memory. And now since the branch predictor is used to the true result, it speculatively executes that piece of code, and it allows for out of bounds memory retrieval. So it allows for memory retrieval and touching bits of memory from other applications, allocated memory, and from operating system memory. So it's just completely out of the bounds of this application's normal processing. Then that memory is cached, and the cache can be, grabbed. Okay. Also, please remember there is no privilege checks on speculative branches, just like on out of order execution. So even if it's touching privileged memory, it doesn't matter because the speculative the processor believes that the speculative branch doesn't have any power, and so it allows data to be touched and cached, cached because of the vulnerability, without doing any privilege checks. And then when it reverts that code, like when it says, oh wait, that's out of bounds, I can't do that, or oh wait, that's a false statement, I'm not going to run that piece of code, it doesn't actually revert the caching of that bit of memory. So, like I said, I'll go through this code a little bit deeper. So that piece of code right here, that piece of code will grab non-secret memory addresses. So it'll just usually grab memory within the processors or within the application's allocated bank. But that's only when x is less than array 1 size. When it's greater than, it grabs secret memory addresses and information from other applications. Normally, this information is protected by privilege checks, but once again, that doesn't happen on speculative instructions. And as we learned in Meltdown, and as I just said, touched memory is cached and cached memory is accessible. So, the problem with fixing. So, patches for these vulnerabilities aren't like any other vulnerabilities. These vulnerabilities aren't like any other vulnerabilities. They're completely new. They fundamentally change how computers need to be built and how we run applications and make processors. So some of these patches on some systems will crash the system. Some of them on other systems will slow the system down significantly, and I do mean extremely significantly, to the point where while you should update your PCs and your desktops and everything, ideally to protect against these attacks, it's almost not worth it because of how much slower your computer will be. Patches are really more meant for, at least right now, are really meant for cloud providers, cloud service providers. So like Amazon had to add a bunch of servers to make up for the speed loss that came about with patching. And so did Google, and so did Apple, Microsoft, etc. If you have a large amount of servers and lots of virtualization, you need to patch. But you'll also have to add more servers to fix the problem of slowing down. So, all is not lost, everybody. I know it looks pretty dismal, but don't worry, somebody made a version of Doom that is secure against Meltdown and Spectre, but it loads one frame every 7 hours, so there's some performance issues. So there's the GitHub link to that. And here is some live gameplay. This is actually just a still image, but if you wait 7 hours, I'll probably have time to switch it. Alright, so like I said earlier, I can't really run my actual live demo, so I'll just show you exactly where I got it from, and I'll explain the images here. So, this is the really important part right here. So normally when you want to run something with privileged access or admin access in Linux, you'll write sudo beforehand. So as you can see, there's no sudo here, which means that this is being run just in user land. And it's reading information from another process. So basically what this program is doing is starting a process that's storing the string that says the magic word, and then it's running another process of the Spectre attack that's grabbing that string. So it's stealing this information from another process's memory, so these are the memory addresses, and the magic word, without any administrative privileges, which is a pretty big deal. So here's Meltdown. Once again, there's no sudo, so you're not running it on admin, but what is it doing? It's taking kernel information, so the version and the build information from the kernel, which is from privileged operating system memory, and it's printing it out. So it's accessing these privileged memory bits, memory addresses, with userland code, which is a pretty huge deal. That's all I've got for you. My email address, if you guys want any more information, is Daniel, D-A-N-I-E-L, actually, why don't I just write it here? Daniel.bloom@okstate.edu. You should come to ISAC every other Thursday, 6:30 p.m. Dr. Berkman will give you the rest of the details. Alrighty. Thank you very much. Have a great day.